Okay, so let's look at 15 and 16, the final two problems on this portion of the handout. So first, some rationale, because you've seen you can do the proofs from several different ways. When everything else in the problem has an angle of x, but there's one particular thing that has an angle of 2x, I really want to think about replacing that one particular thing so that the angle matches everything else in the problem. So that's why I chose to start on the right side, because I felt like I was going to make a substitution there. Now, cosine of 2x, if you look up your identities, has 3 different ways to replace it. And I definitely wanted to replace it with something that had 2 terms in it. And you can actually do it several ways in several different replacements. Why would I do this one? There's a minus sign, and in my head, I'm kind of thinking that secant means cosine in the denominator. So if I have a sine somewhere in the numerator, I have a better chance at making tangent. So that's how I chose this 1 minus 2 sine squared x. So then my next step is to distribute the secant to each of the terms. So secant squared times 1 makes secant squared. Secant squared times negative 2 sine squared x is negative. So again, I'm multiplying secant squared x times negative 2 sine squared x. Remember that secant squared is 1 over cosine squared. And since this is all just multiplying and there's no addition and subtraction, we can think about this as one fraction. When we do that, you see that you have a sine over a cosine with the same angle. Sine over cosine is tangent. They're both squared, so that's a tangent squared. So that's why I'm getting the negative 2 multiplying by tangent squared. I now feel pretty close because the identity has tangent squareds in it that I'm trying to get it to prove equal to. However, it doesn't have secant squareds in it, and I still have that term. But I remember that there's a Pythagorean identity that says that secant squared is equal to 1 plus tangent squared. So again, that identity says that secant squared x would be equal to 1 plus tangent squared x. So I want to take out the secant squared x and replace it with 1 plus tangent squared x. So that's what I did right here. I didn't change that second term, so it's still there. And now all I did was combine like terms. The like terms here are the terms that contain tangent squared x. So really when I look at them, there's a 1 tangent squared x at the beginning. There's a regular just constant of 1 in the middle, which would not be a like term with these. And then there's a minus 2 tangent squared x. So notice those both have tangent squared x. That's what's making them like terms. So I really just want to add the coefficients of 1 and negative 2, and that's giving me negative 1. So this 1 remains right here, and this minus tangent squared x came from my combining of those 2 like terms. So looking at 16, I'm looking to see something similar. So here's what I see going on. Both sides in this case have a 2x. But this side also has angles of x. So here's kind of my path to success that I'm going to see. I know I need to combine some of these together or substitute them. I can't do them when one angle is different. So I'm going to look to substitute that angle, but I'm probably going to have to resubstitute something back in at the end to turn it back into a double angle. Okay. So as I look to simplify what I have here on the left side, one of the first things that I did was I multiplied these 2 things together. Tangent x times cotangent squared x. So remember that cotangent squared is like having 2 cotangent x's. And remember that cotangent x's are the reciprocal of tangent x. So really, it's all of this multiplication that's happening. So one of those, tangent x, and one of the tangent x factors in the denominator cancel out and just make 1 and leave me with 1 over tangent x, which again is a cotangent. So that's why when these 2 things multiply together, I just have left cotangent, and it's still multiplying that other factor of sine 2x. The next thing that I did was work on swapping out for an identity this double angle so that it had just the single x in it like all the other angles, so I could find more things that could cancel out. So I used the identity for sine of 2x, which is 2 sine x cosine x. That means this is all in the numerator. It's multiplying cotangent, which is cosine over sine, and those have a common factor of sine in the numerator and denominator, which cancels out and gives me 2 cosine squared x. So that's really simple. If I was just looking to simplify the left side, I'd probably leave it just like that. The issue is I want it to look like the right side. And notice on the right side, there's an addition problem and there's a double angle. So I have to make some sort of substitution here that's going to give me two terms. So the only thing I can substitute for cosine squared from the Pythagorean identity is 1 minus sine squared. Having done that, I can distribute the 2. So that's why I have 2 minus 2 sine squared x. And this is a little bit tricky. I want to think of 2 as two parts, a 1 plus another 1, and then I have this other term of minus 2 sine squared x, because this group of things being added and subtracted is an identity, but not with this extra 1 being added in there. So it is kind of weird to think of 2 as 1 plus 1 instead of leave it written as 2, but I did that because I knew I was trying to get a double angle identity, and the only double angle identity I knew for cosine of 2x was that contained sine squared, since that's what I had, was the 1 minus 2 sine squared x. So I was really trying to get this in my problem, and I was so close. I just had this 2 here. So that's why I split the 2 up into 1 plus 1, so that I could have this piece that I wanted with an extra 1 being added to it. So this 1 stayed, and this terms together became that identity for the double angle.